Hello, my name's Christine, and I'm going to be talking about a project I worked on with Hai Leung, Hegde, Long, and Faith at NASA's GES DISC. I'm going to be talking about how we moved our gridded geospatial data into point data to simplify our analytics, which actually came about sort of as a side effect of our move to the cloud. So, some background. The GES DISC is one of 12 Earth science data archives at NASA. We focus on data sets related to atmospheric composition, so things like carbon monoxide or NO2, data sets related to water and energy cycles, so things like precipitation, and data sets related to climate variability. So these are generally model data sets going back 30, 50 years. In addition to archiving this data and providing this data for free to anybody who would like it, we provide data services to make the data easier to use. One of the popular data services we provide is Giovanni. And actually, it's very cool. This year marks 20 years since the first public version of Giovanni went live. And the purpose of Giovanni is to simplify the path from the data sets we have to usable science. Many of the data sets we have are a little bit difficult to use. The data formats are not something that everybody is necessarily familiar with. And the way the data is organized is often more related to the way the data comes down from the ground and is processed than it is related to the way end users may want to use that data. So Giovanni lets our users visualize data in a web browser without having to download anything. So they don't have to go in search of data, download files, try to find tools that read that data, and then try and visualize something. With Giovanni, they can get some simple summary statistics plots in a browser without having to download anything. On the left, you can see our interface to the current operational Giovanni. Through this interface, you can select one of 22 summary plots. Most of these summary plots are averages. Then you can select a date range and region of interest. In this case, I have selected the time and area of Hurricane Katrina along the Louisiana coastline. Then you can select one or more physical parameters out of our 1,000 physical parameters. These parameters fit into about 50 different kinds of measurements, where a kind of measurement would be something like soil moisture or precipitation in this case. And these physical parameters come from more than 20 measurement platforms and instruments. On the right, I'm showing you our two most popular plot options. So the upper right is a time series of precipitation over the Louisiana coastline during Hurricane Katrina from back in 2005. Each point on this time series is the average of the precipitation over the Louisiana coastline at that time. But sometimes you don't want to see sort of when the precipitation hits. You want to see where the precipitation hits, in which case you can take a look at our time averaged map, where every pixel on the map is an average across time of the precipitation at that location. Our current on-premises Giovanni is, the technology stack is more than 10 years old. And the server, the web page is served from a single server. The problem with this is that, first of all, because the technology is older, it becomes more and more difficult to find people to support that technology because, people aren't really learning Perl these days, just as an example. But more importantly, our server can't handle surges in load very easily. So if it is, the day before AGU posters, abstracts are due, then, sometimes we can get more people coming in than we can handle. Or if somebody has a class where they want all of their students in the class to try and do the same plot at the same time, then we can run into problems. And again, in part because the technology stack is older, it doesn't scale well to multiple servers. So we don't really have the option of simply taking that technology as it is written and expanding it to have access to more compute when we have higher load. So we decided about 3.5 years ago to start heading in the direction of the cloud to address some of these issues. And when we decided to do this, probably our first question was, what data format are we going to use? Giovanni is completely data-driven. With no data, you have no plots, you have no points. So figuring out what data format we were going to use was kind of our central task. I think data storage in the cloud is something that a lot of people now have dealt with. But for those who haven't and maybe somewhat unfamiliar with it, just know that if you have a large data set that you want to store in the cloud, generally speaking, that's going to mean that you're going to put it in object storage, because doing anything else is going to end up being quite expensive. And if you have data in object storage, then the libraries you use to access that data obviously have to support the object API. And furthermore, the data formats that you're using really need to be kind of subsettable in place. Because you're putting this data in object storage, every time you pull data out, you're pulling it over a network. So you want to only pull over the bytes of data that you really need. You don't want to pull over the whole thing, or you're going to have a lot of performance issues. So just a little bit more background. If you look today at the GES disk and you look at the file formats, the data that we archive, you will see that the data is basically all in HDF5 or NetCDF4. And these two data formats are actually very related to each other. NetCDF4 is HDF5 under the hood. I have here a NetCDF file that I've opened up in a tool called Panoply. And what I want you to be able to see is in this one file, I have multiple variables. The first variable is our sort of, you could think of it as our data variable. It's the actual precipitation variable. The other variables are related to the latitude, longitude, and time. The other thing I want you to see is that the data variable, and actually the other variables, have metadata associated with them. This metadata allows you to associate the data variable, the precipitation, with its dimensions, latitude, longitude, and time. So these are self-describing data formats, and it's very nice because you can open the file and get all the information you need to be able to interpret that data variable. So the data model underneath is, for the kind of data that we have in Giovanni, a sort of multidimensional data array where the dimensions are latitude, longitude, and time, and then associated longitude, latitude, and time variables that tell you where and when that data is from. The problem with HDF5 and NetCDF4 is that unfortunately they are not currently very cloud friendly. The libraries don't support object storage, and the data format means that you can't subset it in place. So I should mention that HDF5 has a cloud effort called HSDS, but it's basically a data server cluster that has to be up anytime you want to get that subset of data. So that's quite a lot of overhead. So when we were looking into this about 3.5 years ago, there weren't really all that many options for cloud-friendly, cloud-native data formats. Most of the data formats, I think all of the data formats we found, were part of the Hadoop ecosystem, including Apache Parquet, which was released back in 2013. So it's had quite a long time record for a cloud-friendly data format. It is a columnar data format, which I'll talk a little bit more about in the next slide if you are unfamiliar with that format. Apart from the fact that it was cloud friendly, one of the things that we really liked about Apache Parquet was its very simple data model. NASA Earth Science has this concept of levels of data from level 0 to level 4, and it doesn't really matter exactly what these levels mean, but the different levels tend to have different internal structure, and several of those levels can be successfully modeled with this simple data model in a way that kind of erases the distinctions between levels and formats of data, which we thought was really nice. So as I mentioned, Apache Parquet is a columnar data format. What that means is, in terms of the data model that you see, it's basically a giant table. You can think of it as like a table you'd see in a database. So that means there's no multidimensional arrays. So how do we take our multidimensional array data and put it in this data frame table format? What we did is we basically had to flatten our multidimensional arrays so that every row in our Apache Parquet table had one data value and then the associated longitude, latitude, and time. And effectively, this made our multidimensional arrays into point data. But that's how we did it. Now, you might look at this and think, oh my gosh, look at that time column, or the latitude column, or the longitude column. You're replicating the same latitude and longitude values over and over again in different locations in the table. But Apache Parquet compresses very nicely, so you don't actually end up with enormous files. So how did it go? We made this big change. What kind of performance results did we have? I'm going to show you some example results from a long time series, 10.5 years, of global averages for each day. The underlying data set is a daily data set, 0.1 degree data. So the entire calculation involves a little bit less than 25 billion points. When we ran this time series using our on-premises Giovanni, it took 4.5 hours just to calculate the time series. And when I decided to go and dig through our code and find just the files associated with calculating this time series, I found about 4,000 lines of code. And, I should say that this also includes like comments and white space and stuff. But the point is, it's a lot of lines. The first example I'm going to show in the cloud uses Dask with Apache Parquet files sitting in object storage. For those who are unfamiliar with Dask, Dask gives you scalable analytics, and you can run it in a cluster or you can run it in a single thread. In this case, for this example, I did run it in a cluster, but you don't have to. So when I ran my time series using Dask, I got a result in 1.5 hours instead of 4.5, so 3 times faster, which was great. But probably even more impressive is that I went from 4,000 lines to 75 lines, which is amazing, right? That's 50 times less code. And, this isn't the whole 75 lines, but this is the function that tells Dask how to calculate the time average. And you can see that it's just ridiculously simple code. I could hand this code to anybody who writes software and they'd understand what was going on in like 5 or 10 minutes. It's fabulous. The other example I'm going to show you is using AWS Athena with Apache Parquet files in S3 using a 3-dimensional accumulation trick. So if you haven't ever run across this trick for speeding up averages with accumulation, it's a very simple principle, but I'm just going to go over it quickly here. So for the sake of simplicity, suppose you have a 1-dimensional data set with values like this. And suppose you want to calculate an average over values at positions 5 through 8. You would add those 4 values together, divide by 4, and you have an average, right? This is how we calculate an average. But what if you know that your averages are always going to be over contiguous sets of values? Because, just as an example, you're calculating an average over a contiguous bounding box, or you're calculating an average over a contiguous time period. What can you do to speed this up? Well, rather than storing the original data values, you can store an accumulation, which is the sum of the data up to that point. So in your accumulation array, the value at index 1 is the sum of the data at indexes 0 and 1. The value at accumulation position 2 is the sum of data at position 0, 1, and 2, and so on. And what you might notice about this accumulation array is that at position 8, we have the sum of the data from positions 0 through 8. So this isn't quite right. We want the sum of the data from 5 to 8, but it's close. And you might also notice that we have at position 4 the sum of the data from 0 to 4. So this combined helps us to calculate our average. So what we can do is take the accumulation at position 4 and subtract it from the accumulation at position 8, divide by 4, and voila, we have our average again. And what's so nice about this is we have a constant time algorithm, right? I mean, it doesn't matter how many points we are calculating an average over. We only ever have to do that one subtraction in order, and then, obviously the division, but basically one subtraction, one division, and we're done. So our data, of course, is not one-dimensional. It is three-dimensional, but it turns out that you can extend this general principle to an arbitrary number of dimensions in accumulation. And in general, you're going to need at most 2 to the n points to calculate your average. So for us, we have 3 dimensions, latitude, longitude, and time. So we need at most 8 points. And what's beautiful, again, about this is that this is still big O of one constant time, because no matter how large a region or time range we're averaging over, we still only need 8 points. So when we use this trick with AWS Athena, which allows you to sort of build tables from this Apache Parquet files and then write SQL queries against it, we were able to calculate our average in an impressive 5 seconds. When we first saw this number, I mean, we were amazed. 4.5 hours to 5 seconds, right? That is fabulous. 3,000 times faster. And even though our code was a little more complicated than a Jupyter notebook, because this code that I'm talking about here is actually like, production-ready code, it was still only about 300 lines of code, so still a significant reduction in complexity. If you want some more details on how we did this multidimensional accumulation, I highly recommend you go and take a look at this poster, which my colleague Hai Liang presented at last fall's AGU meeting. He's the one who implemented all of this stuff, so it's a good poster to look at. So in summary, when we had Dask with Apache Parquet, our code complexity went way, 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 way down, and our speed went up, with a caveat that it went up sometimes, which I'll explain. When we used AWS Athena with Apache Parquet and accumulation, our code complexity still went way down, and our speed went way, 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 way up. So at this point, you may be wondering why I'm kind of comparing apples to oranges here. Why am I not telling you what happened with Dask and Apache Parquet with the accumulation trick? Well, unfortunately, it turns out that when you're running Dask against Apache Parquet, it doesn't do subsetting very well. So an awful lot of that hour and a half that I quoted for doing the the area average, was actually kind of involved in doing the subset. So when you're doing accumulation, it's almost the ultimate subset because you're only pulling out 8 points. And, with Dask, it just wouldn't have very good performance. I should mention that my colleague Hailiang looked into this to see if he could speed it up. And what he found is that he could sort of set the data frame divisions based on what he knew about our Parquet file formats. And then he could also calculate the offsets into those divisions and then get the data out, and that was pretty fast. But then you couldn't use the main Dask API. I was kind of like, well, then why are you using Dask in this case? So on the other hand, why not show AWS Athena with Apache Parquet without the accumulation trick? Here, the answer really is cost. So AWS Athena charges you by something called scan size. And so if you're calculating averages over 25 billion points, it charges you to scan those 25 billion points as part of the calculation. If, however, all you do is pull out 8 points per time slice, it's not scanning nearly as much data. And furthermore, the subsetting is actually very quick with AWS Athena for whatever reason. So you end up with something that is both fast and quite cheap. So in conclusion, when you have Apache Parquet as your data format and you have a high-level specification to define your algorithm, you end up with this really effortless parallelization. In something like Dask or AWS Athena, you just say how you want something to be calculated. You don't have to tell these systems exactly how many workers or tasks they're going to have available to them. They figure this stuff out for you. And that's one of the reasons why the specs end up being much shorter than the code we had to write for our on-premises version, where we had to manually code all this parallelization ourselves, which was a real pain. The other thing is that when you have data frames, when that's your model, is this sort of table or data frame, you end up with just really nice and simple code. It's not that dimensions are horrible and having multidimensional arrays is the end of the world, but it just complicates the data model. So if you don't need to worry about them, it's really nice to not have to worry about them. So where do we go from here? As I mentioned, we made our decision to go with Parquet about 3.5 years ago. At the time, Zar was like a brand new project as far as I know. We hadn't heard of it. I think we first heard about Zar 2.5 to 3 years ago. But now that it's been out there for a few years, we are taking a second look at our data format and looking very seriously at Zar. Zar is a cloud-native data format, cloud-friendly data format. It allows you to have multidimensional arrays, which is nice for those cases where you need multidimensional arrays, and they're useful. So cases like, for example, when you're doing regridding and you need to know which data points are next to each other in time and space. It also, especially if you use it in conjunction with Xarray, supports metadata. So it ends up looking a whole lot like models that we're very familiar with from NetCDF and HDF, and our science teams are very familiar with because they've been working with this, for years. So the only sort of downside we've seen to Zar is kind of library support and sort of standards. As far as we can tell, Zar is quite strongly tied to Python, which is okay. I mean, look, we love Python. We write in Python all the time. But we know from experience that sometimes you find yourself needing to write something in a different language for various reasons. And we're a little worried that we may, run into trouble if the only thing we can use is Python with Zar. But still, we're really looking at Zar and liking Zar at the moment. Thanks for listening, and thanks to NASA's GES DISC for supporting this work.